All right, in this video, we're going to look at these examples on page 6 of the 9.2 slides. This first example is to find the steady state distribution vector for the regular Markov chain whose transition matrix is t equals 0.7, 0.3, 0.2, 0.8. So to do this, we let x be the vector xy, and that's what we're looking for. We're looking for those x's and y's. And we take tx equals 0.7, 0.2, 0.3, 0.8 times xy, and we want this to be equal to xy. And that's equivalent to this system of linear equations, 0.7x plus 0.3y equals x, and 0.2x plus 0.8y equals y. You know what? I reversed two of these. That should have been 0.7x, 0.2y, 0.3x, 0.8y. Okay, well, and each of these is equivalent to the single equation 0.3x minus 0.2y equals 0. We do that by subtracting x and y respectively from each of these equations. So if I subtract x from both sides of this equation, I get 0.7x minus x plus 0.2y equals 0. That gives me negative 0.3x plus 0.2y equals 0, which is the same effectively as 0.3x minus 0.2y equals 0. So this is an equation that we can use, and we're going to solve that for blah blah blah. Well, we'll take a moment there. We'll get back to that in a moment. We also know that x plus y must equal 1, not 0, 1. That's just the sum, the condition that the sum of the elements of x must be 1. Okay, so since we know that this right here is the same as 3x plus 2y minus 2y minus equals 0, so I can subtract 3x from both sides and divide both sides by 2. Are we doing it the other way around? Let's do it the other way around. We're going to add 2y to both sides to get 3x equals 2y, and then divide both sides by 3 and get x equals 2/3 y. So since x equals 2/3 y, I can substitute that in here to get y. That's 2/3 y plus y equals 1. Well, then 2/3 plus y, 3/3 is 5/3 y is 1. Well, then y equals 3/5. I just do that by dividing both sides by 5/3. If y equals 3/5 and x equals 2/3 y, then x equals 2/5. And certainly 2/5 plus 3/5 equals 1, so that satisfies that condition. And now we have our vector that makes this true. X equals 2/5, 3/5. That's our x vector, not our x variable. There we go. And if we plug this into our original matrix multiplication, we'll see that it's true. And we can rewrite this as 0.4, 0.6, which we may remember from an earlier problem. If we take 0.7, 0.2, 0.3, 0.8, and multiply it by 0.4, 0.6, 0.7 times 0.4 is 0.28. plus 0.2 times 0.6 is 0.12. 0.3 times 0.4 is 0.12. 0.8 times 0.6 is 0.48. 0.28 plus 0.12 is 0.4. 0.12 plus 0.48 is 0.6. And there we go. So we got one more problem we want to do here. Same sort of problem. Lining that up just right. And let's take a look at this one. The transition matrix T below describes the movement of taxis from zone to zone. Use this information to determine the long-term distribution of the taxis in the three zones. And we're going to do exactly the same kind of thing. Our T matrix is what we just saw, 0.6, 0.3, 0.3, 0.1, not 0.3 there, 0.4, 0.3, 0.3, 0.3, 0.3, 0.4. Okay, and we let x equal the vector of x, y, z. And we're trying to solve this matrix equation. Tx equals x, or equivalently 0.6, 0.3, 0.1, 0.4, 0.3, 0.3. Lights just went off again. 0.3, 0.3, 0.4 times x, y, z equals x, y, z. Give me one moment. I get the lights working again. There we go. Okay, so this brings us to a series of equations by multiplication. 0.6x plus 0.4y plus 0.3z equals x. 0.3x plus 0.3y plus 0.3z equals y, and 0.1x plus 0.3y plus 0.4z equals z. But that is equivalent to this system of linear equations: 4x minus 4y minus 3z equals 0. 3x minus 7y plus 3z equals 0. And x plus 3y minus 6z equals 0. Also, we know that x plus y plus z equals 1. So we need to solve this system of equations. We can use the Gauss-Jordan method, but we don't really need to do that in detail here. We can just use this. We just say that we've solved this, and we get x equals 33 over 70, y equals 3 over 10, and z equals 8 over 35. In the long run, approximately 47% of the taxis are in zone 1, 30% in zone 2, and 23% in zone 3. That is it for this video. If you have any questions, please get in touch.